So the idea behind clustering is to group data points that are similar, right, and try to keep them as far away from things that are dissimilar, etc., right. And I said that a lot of conveniences to looking at the clustering problem as it is done on a graph, right. And we talked about hierarchical clustering. We said you could do minimum spanning trees, okay, and then you could do all kinds of like single link, complete link clusters. You could form that using graphs, right, looking at thresholded graphs, etc. So we looked at a variety of different things you could do with graphs, right. So it turns out that increasingly graph based clustering is becoming more and more popular, right. We talked about density based clustering and we said it could give you kind of arbitrary kind of clusters, right, and also we talked about Cure and we said Cure could also give you non convex clusters and things like that. It turns out that if you use what are called spectral methods for clustering on graphs, right, you get all of these in a very natural way, right. You get all kinds of weird clusters in a very natural way because essentially you are looking at graphs here, you are not really looking at any kind of metric space, right, and as long as you have represented your data in a graph, right, you can do the clustering on it. So how do you get your data into a graph? Did we talk about constructing graphs out of your data? So somebody tell me how you get this, right. So the first one is you can do something like you can do what is called epsilon neighborhood graph. So what you do is you take a data point, right, draw a circle of radius epsilon around it and any point that is there in that radius you connect it, right. So this will be a symmetric relation. So if A is within epsilon of B, then B will be within epsilon of A. So it will be a symmetric relation. So you typically graphs that are constructed this way are undirected graphs, right. Graphs that are constructed this way are undirected graphs. And then the second thing is typically graphs that are constructed this way are also unweighted graphs because epsilon is usually small, right, and the differences in the distance also will be even smaller than epsilon. So you do not really want to focus on those differences in the distances, you just go ahead and assign them all the same weight, okay. So is it clear? So what you do with epsilon neighborhood, you essentially end up with an undirected unweighted graph typically, right. The second thing you could do is called the k nearest neighbor graph. So what do? I take a point, I find the k nearest neighbors to that point and connect them, right. Now here is the question, is this relationship symmetric? Not necessarily, right. So A could be one of the k nearest neighbors of B, right, but B need not be the k nearest neighbors of A, right. So it could be slightly, there could be more neighbors that are clustered around A and so B might not fall in the k nearest neighbor list. So typically these graphs should be directed graphs, so there is an edge from A to B, that means B is within the k nearest neighbors list of A, right. So and then if there is edge from B to A also, that means that the relationship is reciprocal but otherwise not, right. And also the nearest neighbors, k nearest neighbors could be very far away, right, the distance need not be uniform. So typically you use a weight, right. So the most general form of this k nearest neighbor graph should be a weighted directed graph, right. In the epsilon neighborhood case it will be an unweighted undirected graph, in the k nearest neighbor case it will be a weighted directed graph, but for reasons of convenience and because there are a larger class of methods that operate with undirected graphs, right, we tend to treat the k nearest neighbor graph also as an undirected graph, essentially we ignore the direction on the arrows, right. So if there is an edge between A and B, it means that either A is a k nearest neighbor of B or B is a k nearest neighbor of A, well, or both. I mean, it's an inclusive or, right. So both is fine. So that's essentially what will what we will do normally, right. So we actually even treat the k nearest neighbor graph as an undirected graph, and so the third mechanism is we are already given the graph, right. I told you that you are just given the similarity measures between the nodes, you are not really given the data points, and from there you can construct the graph, right. So sometimes you essentially end up with the complete graph. So in this case you have to give weights, right, otherwise it does not make sense. So the complete graph will be a weighted graph, right, and it just says that okay, I will connect points A and B and the weight will be proportional to or inversely proportional to the distance between A and B, right. So weight will be inversely proportional to the distance between A and B, right. So that means every point A and B will get connected. If they are very very far away, they will be connected with a very small weight, but still they will all be connected, okay. So this is essentially, these are the three ways in which people typically take the data that you have and convert it into graphs, okay. So now what we do with these graphs, right. So I will start off with a simple problem that of trying to split this into two parts, right. I have data, I want to split the data into two parts, okay. So some notation, it is an adjacency matrix, right. So I am going to assume that this is a symmetric matrix for the time being, okay, and yeah, so in fact all the three could be considered as symmetric matrices, right. If I am going to convert all of them into undirected graph, all of them will be symmetric. So I am just going to think of this as a symmetric matrix, right. I am going to define the quantity called the cut value denoted by R So the cut value is essentially, I will sum up all this Aij such that I is in one group and j is in the other group, okay. So I have a graph, I have a graph something like this, let us say, and I divide that into two groups, that is one group, that is another group, right. So I am going to sum up all of these such that I is in one group, j is in the other group, right. Let us give them numbers so that we can do some some arbitrary numbers. So what will I do? So this sum will run over A15, A16, A17, A19 and A18, well all of them happen to be 0, so we do not care, right. So likewise A25, A26, A27, A28, A29, so only A25 will be 1, so I will count that once, right. And then for 3, well everything is 0, I do not care, and 4 I will get a 1, I will count that once, right. And what then do I stop? I keep going. So 5 I will count it, so what will happen? 5 again I will get a 1, so I will count it once, right. So 6 I do not care, so 6 will be what? So A62, A61, A64, A63, So all of them are 0. So likewise I keep going, and for 8 I get a 1. Okay. So how many do I count? I count 4. Right? I counted 4, but truly how many edges have I cut? 2, and that is why the half. Okay. So this way I do, when I do this I count every edge twice, right, and some more notation. Right. So I am saying Si is plus 1 if I is in group 1, it is minus 1 if I is in group 2, just an indicator variable. Okay. So one thing, just remember that for all S transpose S will be n, where n is the number of nodes, okay, n is the number of data points, right. So Si is the ith entry in that vector S, okay, which indicates whether the ith data point belongs to class 1 or group 1 or group 2. Okay. So let us look at this expression. So when will L be 1? Sorry? Huh? Both in different groups, right, and they are both in different groups, it will be 1, both in the same group it will be 0. So if I and j are I and j are in the same group, it will be 0. If they are in the different groups, it will be 1, right. Is that clear? I hope it is just a bag and not a person. It is loud enough to be a person. Sorry? No, this is just a assignment here, right. So we just taken some assignment, right, and we are trying to evaluate it. So that, like I said, right, I have arbitrarily chosen this assignment. Right, I could have chosen a different assignment. I could have said 1, 2, 5, 6 are in one cluster, one group, and the remainder are in another group, and I could have evaluated that. Okay, why don't we do that for fun? Right. So what will be the R value here? 5. Right, R value will be 5. So I can just take any cluster, any grouping like this, and I can evaluate and find the R value, right. So my best bet is to find the R value, that is the smallest. When would be the smallest? All of you know the degenerate solution to this problem. When all the nodes belong to group 1 or group 2, right. So the cut will be 0. So we have to avoid the degenerate solution. We will see that it will fall out naturally from here. The degenerate solution will come out as the best solution. So we have to explicitly exclude it. Okay. Great. So far so good. So what are we doing here? We have essentially come up with a mathematical expression that captures this, right, such that I and j are in different groups. So instead of saying that, I could just multiply the terms here by this and sum over all ij. If they are in the same group, the number will get added. If they are in different groups, I will get a 0, right. So instead of doing something cumbersome like this, I can do something more compact, right. So I can write R as okay. So that half, I have another half here, so I get a, so ij run over 1 to n, okay. So one other notation I should introduce. So what is that? Degree, right. If I want to get the degree of node I just sum over j aij, right. So that will give me the degree of node I, okay. So what will be the first term in here? Just aij, right, is sum over that will be the first term for R, okay. I am just going to take that and rewrite that into something more complex. Right. What is sum over ij aij? Huh? Twice the number of edges, but we will write it in a little more complex form so that we can go back, plug it in and derive one nice expression, okay. So this I will write it as summation over I of ki, right. Can I do that? Done, right. Where delta ij is a function that is 1 if I equal to j, 0 otherwise, right. Sounds looks like this, right, but there is a purpose for doing that, but all of you buy this, right. If you are wondering why si squared is okay, si squared is just 1, okay. So I am just multiplying it by 1, so it is fine, and then I am just splitting that into si sj and writing it into a more complex form. Now I am going to substitute it back there, right. So essentially what I have done here is I have produced si sj on both terms, right. Fine. Right. So there is just lot of algebra here, nothing yeah, high school stuff, nothing complicated, okay. So I am going to introduce a new matrix Lij which so the ijth entry of the matrix L will be this, right. So if you think about it, right, I can write this as as D minus A, where D is a diagonal matrix, where the ith entry in the diagonal is the degree of node I, right. So, this expression is sometimes called the Laplacian, it is called the Laplacian of the matrix A, right. It is also called the unnormalized Laplacian of the matrix A. So, the normalized Laplacian, you actually do a transformation on this and it has got better properties in terms of both in terms of clustering and also in terms of other things which people use the Laplacian for, but I am just going to show you how to work with the unnormalized Laplacian in form, right. The actual algorithm for working with the normalized Laplacian is exactly the same as working with unnormalized Laplacian, except that proving things are slightly different, showing that you are getting good clustering is slightly different, right. So, I will give you material to read up on both normalized and unnormalized Laplacians, but we will look at unnormalized in the class, okay. Right. So, this makes sense. So, the Laplacian is D minus A and it is not an arbitrary choice, we arrived at it by trying to say that, hey, I am looking at the cut size, right, and I want something that characterizes the cut size, then we did a lot of algebra after that, we ended up with D minus A, okay. This is not the only way to derive the Laplacian, there are many ways in which many different fields in which people have actually independently come up with something that looks like the Laplacian, right, and then it's got wide applicability. So, how many of you actually used Laplacians before of graphs? Did you say? Not in matrices, okay. I am not talking, yeah, it is very closely related to your Laplacian in the continuous domain actually. So, it's yeah, no, I am not going to get into that, it's just too much. So, we do our matrix notation transformation, right. So, I can say that my cut is just 1/4 S transpose Ls, right. So, Si Sj into Lij, right. So, essentially S transpose Ls. Okay. So, now the goal is choose S such that R is minimized. Okay. So, the development I am following comes from Newman, who is one of the pioneers in looking at graph partitioning and what the social network people call community deduction and so on and so forth, right. I mean, he did not come up with spectral clustering, right. Spectral clustering is older, but so Newman came up with this very nice way of introducing spectral clustering, right, without ever going into real analysis or functional analysis or anything, just going with a little bit of algebra and a little bit of linear algebra. So far we have not even done linear algebra, right, except for that very rudimentary transformation, right. So, just looking at very basic concepts, he kind of motivates how you do the partitioning, right. If you typically go read other things, right, they will start off with say, okay, here are the properties of the Laplacian and we apply these properties and therefore we can solve this like in one shot and here is an answer and things like that. So, it becomes a little more tricky. So, I am going to make you read all of that, but I just want you to appreciate that the idea behind this is fairly straightforward. So, whatever we are doing is fairly straightforward, right. So, now we will enter into the spectral domain, right. So, I want to say Vi denotes a kind of a normalized right. The VI's will denote the normalized eigenvectors of L, right. I can take the S and I can write it as right. So I have the eigenvectors, right, they are going to span my n dimensional space. So I can just take any point S which is in the n dimensional space, I can write it as a combination of the eigenvectors, right. So if you think about it, AI is just essentially standard stuff. Not sure why I need that, but anyway, yeah. So note that S transpose S is what? N, and S transpose S is what? Sum of A squared, right. So that should be equal to N, that is a constraint that we should have in remember that. So now let us go back and make the R look complex again. That is S transpose S, right. So here comes our the fact that Vi and these are eigen vectors of L, right. So what would be L Vj? Lambda j Vj, right. So I can just write it as lambda j Vj, and right. What about Vi transpose Vj? Delta Ij, right. Vi transpose Vj will be 0 if I is not equal to j, right. So essentially what I will be left out with is I mean I could have written lambda I or lambda j, whichever, right, does not matter, right. We have to write lambda j because just stick with this notation that I had the j on the right hand side, okay. Is it fine? So this is essentially equal to so S is a vector, right. So I am trying to express S in the coordinate space defined by the eigenvectors of L. So essentially what I will have to do is take S, look at the projection of S on each of those dimensions, and then write it as a sum of those, right. So that is essentially what AI is on, right. This is clear. This is again basic linear algebra. The only place where we use the spectra is when we went from here to here, right. So I am using the fact that my VI's are going to give me a basis, right, and in fact they are giving me an orthogonal, well they are giving me an orthonormal basis, right, because I am assuming they are normalized. So they are giving me orthonormal basis, and that is why I get this delta ij here, right. And then the only place where I used it is the introduction of this lambda I here, lambda j here, right. So this is clear, right. So why I can collapse the summation back into this, okay, great. So now what we do, so what is lambda here? So I am going to assume that the lambdas are indexed such that lambda 1 is the smallest eigenvalue, lambda 2 is the next highest, and so on and so forth, right. Okay. So now if I want to minimize this expression, right, so all I really want to do is minimize my R. If I want to minimize the expression, so what should I do? So I should choose my A such that the maximum weight is placed on the smallest lambda, right. In fact I should place all the weight on the smallest lambda, right. And what is all the weight, right. So we have that somewhere, right. So summation ai squared is n, right. So I need to keep all the weight on so what is the smallest value? There is lambda 1, right. And what is lambda 1? What is that? If people are wondering what that symbol meant, it was L. So I am just summing up one row of the Laplacian. So what do I get? God, guys, come on. So this will be what? Ki. What will this be? Ki. So each row of the Laplacian would sum to 0, right. If you think about it, what is the diagonal element? The degree of that node, and what the off diagonal elements are negatives of the edges, right. So whenever there is an edge there will be a -1, if there is no edge there will be nothing. So the diagonal entry is degree, and then I will have as many -1s as there are neighbors. So adding up the row will give me a 0. Likewise adding up a column will give me a symmetric. You are thinking so long. Symmetric, okay. So it should give you the same thing, right? Great. So now what does this really mean? The fact that the row sum is 0, what does it mean? All 1 is an eigenvector with an eigenvalue of 0. And with a little bit of additional work you can show that this is the smallest, right, because its Laplacian is symmetric, right, and it also turns out to be positive semi-definite, okay, and therefore all the eigenvalues will have to be non-negative. right. So I mean you can very easily verify that L will be positive semi-definite, okay. And so you know how to verify it will be positive semi-definite, right. Take an arbitrary F, so F transpose L, F should be greater than or equal to 0. So if you can show that for any arbitrary choice of F that will happen, then you are all set, okay. So it is L is positive semi-definite, therefore 0 will be the lowest eigen value. So all we need to do is make sure that you put all your weight on the first eigen value, okay, you are all set, right. So what is your first eigenvector in this case? I mean, so my V1 choice is actually normalized, so it will be divided by root n, okay, 1 by root n, 1 by root n, 1 by root n will be the eigenvector that I am choosing for this in this case, right. So how will I minimize this? Essentially I have to align my S with this eigenvector, right. So I will get the maximum A 1, correct, people see that, right. So what is A1? What is A1? A1 is Vi transpose S. So if I want all the weight to go to A1, essentially all I need to do is choose S in the direction of V1, and what will be S? What will be the inner product of S with any of the other V's? 0. So if I choose it to be in the direction of V1, I get my assignment, but choosing it in the direction of V1 means what? I assign it to all ones, right. This is exactly the degenerate solution we were talking about, right. So taking S to be all ones means I am putting everything in group 1, right, or I can put everything in group 2, does not matter, one of those things, right. So choosing S to be all ones essentially is a degenerate solution I was telling you to avoid, right. So what we should do is we should say that I am going to exclude this because this is a degenerate solution. So find an S for me, right, that is orthogonal to all ones, right, because I have to exclude this direction, I have to look at the space spanned by the rest of the eigenvectors. So that space will be orthogonal to the original this dimension that we are excluding. So essentially I will have to put an additional constraint. I am not only interested in minimizing R, but I want a minimizer that is orthogonal to the all ones. So we want to actually exclude this solution, right. So there are many ways in which you can do this. One simple fix is to say that I will fix the sizes of the two groups to n1 and n2. I fix the sizes of the two groups to n1 and n2. So essentially now I am saying find two groups that minimizes the cut size such that one group has n1 elements, other group has n2 elements, right. So if there is some prior knowledge that you have that lets you decide on this n1 and n2, great. Otherwise what you can do is you can start off by saying, okay, I am going to assume I am going to want a 50-50 split, okay, and then search around that to get a better thing, or you do not have to do this at all, okay, you can try something else, okay, which I will talk about right now, just a second, right. So once we have excluded, right, 1, right, what is the next thing you can possibly try to do? Align with V2, right, try to put all the weight on lambda 2, right, because lambda 1 is excluded for us, so we have to go to lambda 2, try to put all the weight on lambda 2, right. Right. So this is also called the also called the Fiedler vector, Fiedler, Fiedler vector. Okay. So V2 essentially the eigenvector corresponding to the second smallest eigenvalue of the Laplacian is called the Fiedler vector. So what you try to do is you choose your S to lie in the direction of V2. Okay, can we do that? We can't. Why? Why?
Restricted to plus or minus 1.
Exactly. So S is already restricted, right? S can have only either plus or minus 1 entries. So I can't really choose S arbitrarily just to lie in the direction of V2. So I have to look at this space of plus or minus 1s and figure out which is the closest to V2. Right? So essentially what I want to do is I want to maximize right, I want to maximize that, right. Yeah, I mean this is straightforward. Yes, that is either plus or minus 1, right. So I can get this. So essentially the maxima will be achieved, but this is the maxima, right. You can't get better than this. The maxima will be achieved when I am making sure that the signs are all positive, same basically, yeah, signs are all same, right. So I will make sure that signs are all positive or all negative, right. So that is essentially what I have to ensure here. So what I do now is then I look at V2, right, and so this is essentially the ith component of V2. I look at the ith component of V2. If it is greater than 0, I make Si plus 1. If it is lesser than 0, I make Si minus 1. Okay, so that is basically it. So now I have a way of dividing it into two groups, and hopefully, okay, I have a sufficient number that are plus 1 and a sufficient number that are minus 1, and therefore I do not end up getting everything in one class or the other. Usually you will find that that is a very nice, in fact yeah, I will put up some materials on on Moodle, right. So where you can see pictures of the eigenvectors, right. So what does well, what does V1 look like, what does V2 look like, and so on and so forth. So what would V1 look like? Straight line, right. V1 will be a straight line assuming that your graph is connected. Okay, if your graph has multiple components, right, so what will happen is your eigen value 0 will have a higher multiplicity than 1, right. Right. So so the number of components in your system, or number of components in your graph essentially is given by the multiplicity of the eigenvalue 0, right. And the eigenvectors, right, the first eigenvector will essentially be an indicator function saying which node belongs to the first component, right. The second eigenvector will be an indicator function that says which nodes belong to the second component, right. So all the eigenvectors corresponding to the eigenvalue 0 will essentially be indicator functions of which components in the graph their underlying thing belongs to. So essentially it will be something like this, 1 for all this while and 0 elsewhere, right, and then next one will go like this for a while and then it will be 0 elsewhere. The third one will be, so it will be like that. So that's you will see that. So it is not that the first eigenvector will always be flat, right. If you have multiple components you will actually see indicator functions there, okay. And in that case, right, how will you do clustering? Well, your components already give you clusters. The only tricky part is now within the clusters, within the components, do you want to do clustering? In which case, you will have to actually look at the appropriate eigenvectors, right. So essentially, you could either say that okay, I am going to take the disconnected component separately, right, and then find out the Fiedler vector there, okay, and then assign it within that component, right. So you should essentially be doing that. Before somebody asks me what you do for equal to 0, just put it somewhere else. Great. And the second lambda 2, right, is also sometimes called the algebraic connectivity of the graph. It tells you how well connected the graph is, right, and things like that. There are a whole bunch of other things associated with the interpretations associated with each of the eigenvalues of the Laplacian, right, but the second one is the most important one. Okay, great. So far we have been talking about dividing it into 2, right. So what if you want to do more than 2?
So why are we doing this method compared to the previous kind of clustering method?
What is previous kind of clustering methods?
Where we did k-means and all the others. They require very few passes over the data compared to this, right?
What? This requires one pass over the data.
You have to construct the k matrices, you have to construct the s matrices.
Nothing. You take the adjacency matrix. Okay, the whole thing will reduce to this. Take the adjacency matrix. Okay. Compute the Laplacian. Compute the eigenvectors of the Laplacian. Don't even compute all the eigenvectors of the Laplacian. I want you to compute only the second eigenvector of the Laplacian. So there are incremental methods that actually give you the Laplacians one at a time instead of actually doing the the eigenvectors one at a time instead of doing it completely. Right, there are incremental methods which can work on very large graphs, right, and then give you the eigenvectors one at a time, right. You just compute the second eigenvector, right, and then do this. That is basically it, right. So this is step 1. Step 2, right. Well, I do not have a proper step 3 anywhere. Step 3 is essentially finding these, finding the spectra. And step 4 is this. Now, if you are doing it naively, finding the eigenvectors of the Laplacian is a very expensive operation, right. So that is a problem, right. So 1 is not cheap. Step 1 is not cheap, right, but it is a one time computation. You do that at the beginning, right. So you do that at the beginning, it is not iterative, you do that at the beginning, you can store this, right. So if you have 1, right, some of the other methods also become little easier, but not k-means, because in k-means you have an arbitrary point somewhere, in every iteration you have an arbitrary point which is the centroid, and now you have to find the distance to that arbitrary point. So you will not be able to minimize this, right. Here you are not introducing any arbitrary points, only the fixed endpoints that you have, and you can find the distances between the fixed endpoints and use any one of those methods and get my adjacency matrix, right. And once I get the adjacency matrix, I just do a this is fairly trivial, right. This is fairly trivial, and then after that I do this is again time consuming, but once I have done that, this is again fairly trivial and I get the clusters. Okay, so the advantages are it tends to give you a lot more varied clusters, there is no restriction on the shapes of the clusters that you are finding, right. So you can find all kinds of different shapes in the cluster, there is no implicit assumption about that, and it turns out to be incredibly robust to small noise and things. So there are lots of nice properties to spectral clustering, right, and therefore that's one of the reasons it's becoming more popular nowadays. There's lots of tools and packages are available. It's not like you're doing multiple passes over the data. In fact, over the data you will do one pass when you construct your Aij, right, and after that it is all operations with the adjacency matrix. So it does not matter how large a dimension your data was in, right. You do one pass over the data, right, or well however cleverly you want to organize it, right. You fiddle around with the data once and you get Aij. Now that becomes the dimensionality of the data points. So your data could lie in a p dimensional space, right. So p could be far larger than n, right, but I will be working only with the n dimensional data. But typically when is far larger than p, sorry, image data, yeah, in image data p is far larger than n, is it? Yeah, depends on how you count p and n, I suppose. Yeah, but yeah, typically p is far larger than n in like working with image data. So in many of these domains where you have this kinds of structure, spectral clustering is a lot more helpful, right. And I also got a lot of cool theory, right. In fact, you know exactly where you are approximating, right, even though you cannot tell by how much you are approximating, right, but at least you have some kind of an understanding of what is going on. And k means well you have EM to guide you there, but so you did the EM version of k means, right. Right, so you have EM to guide you there, but still it is a rough approximation, right. So all of this is confusing, but you really have to do only these 3 steps to get your clusters. Okay. So one thing I forgot to mention here before I go on to multiple clusters. So what if you have the sizes fixed to n1 and n2? Right. So what will you do then? So can you just do this Si equal to +1 if it is greater than or equal to 0 and -1 if it is less than 0? You can't do that, right. I might have more I might not be able to match the n1 n2. So what do I do in that case?
Compromise on those s with small means.
So I start off from the most positive end, right, and I keep marking everything as 1 until I reach n1, right, and the remainder I say is n2, I mean the cluster 2. Does that make sense? Start off, I order the points from most positive to most negative eigenvector component, right. Start at one end, right, I start at the positive most positive end, right, and I say everything is +1 until I reach n1 points, and then the remainder I will say is -1. Alternatively, I can start from the most negative end, I can keep going until I reach n1 points, no, not n2 points, that is the same thing, okay, until I reach n1 points, right, and then assign the remaining n2 to +1. Right. These are actually 2 different ways of splitting the graph, right. If I had gone from the most negative point and gone up to n2 and then assign the remaining to n1, that will be the same, right, but if I choose the n1 either from the top or from the bottom, so I will actually get 2 different split points, right, so I will get 2 different clustering. So which one do you pick? Huh? Whichever one has the lower R, right. So now that I have a measure of comparing, I will just compare R, whichever one has the lowest R, I will pick that, okay. So this Vi2 is there, right, so I will order it the most positive Vi2 to the most negative. So what is Vi2? The ith component of the second eigenvector. So I will take that component wise and I will sort it so that the most positive is at the top and the most negative is at the bottom. Okay. So how do you do multiple clusters? One way to do it is to repeat, divide the 2 clusters, right, divide it into 2. Now I have 2 graphs, right. So once I have done the separation, I have 2 graphs, and in each of those graphs I can go and divide it into 2 again, right. Can I reuse the same eigenvectors whatever thing I have done? No, typically no, right. So I will have to essentially redo everything all over again, right. I would have changed, even though a lot of the connections are still the same, right. I would still be having some submatrix preserved, right. I will still have some submatrix preserved, but because I have chopped off some of the entries, right. So I will have to redo the computation again. Okay. So I essentially have to redo this again, find the Fiedler value for that reduced graph, and then proceed. Okay. Is that a satisfactory solution? Maybe, maybe not. Now when I say divided into 2, I mean you might have made choices, right, which you do not want to do, which you could have made a different choice if you say divided into 4 in the first place, or divided into 3 in the first place. So 3 is even worse, right. So what would you do if you have 3 clusters? So which one of the 2 will you split into 2? So I start off by dividing something into 2, right, and then I want 3 clusters, so I have to pick one of them. So I can pick the larger one and divide it into 2, but that might not be the right choice, right. Then you can argue saying that no, divide both into 2, whichever gives you the better cut value, take that, right, and leave the other one as a whole cluster, right. You could do that, you can think of all kinds of heuristics to do this. So typically this repeated division is done, right, when you are looking to split it into some nice powers of 2, right, and quite often this is something which people use when they are looking at VLSI layouts, right, when they are trying to look at layouts on the chip and then they want to do some kind of segmentation of the circuits that they want to put on the chip, right, they typically end up doing something like this. So the reason they want to do this is, so I want to put 2 things far apart on the chip, I better have few wires going across, right. So these are the lines that I am cutting, right. So they want to keep this as small as possible, right, the number of wires, longer wires I have to draw, they want to keep these things as small as possible. So they essentially do this kind of repeated clustering, and they use spectral clustering a lot in that. So what people do is, I am just going to tell you what people do, I am not going to actually explain why that is a good way of doing it, I am going to let you read it up. So what people essentially do is, they do k-means clustering. I want k clusters, okay, they do k-means clustering, but in a different space. What they do is, they take the data points, right, they do all of these things, right, and then they compute the top k eigenvectors, right, they compute the top k eigenvectors, and each data point, right, each node in the graph that you had originally will get transformed to a point in a k dimensional space. So what would that mean? Suppose I have data point I will be represented by V1i, V2i, V3i all the way to Vki, right. So essentially I will be arranging the k eigenvectors and then reading off the rows to get my data points. So is it clear? Right, so I will essentially be doing this. So V1, V2, V3, no, they are column vectors, right? Yeah, okay. This is actually a matrix, right. So V1 runs like this, V2 runs like this, V3 runs like this. So then the first row here is essentially my representation for data point 1, the second row is the representation for data point 2, the third row is the representation for data point 3, and so on and so forth. So I take all of these things and then run k-means on that space. It turns out that if the graph originally had good separation, if the data itself was originally nicely separated into k clusters, right, if there is some way of separating them into k clusters, then the data points in this projected space, right, will be well separated. I will very clearly see k groups. So it is easy for me to recover this with k-means. Right. So k-means gets confused if you have all kinds of, if your representation is not proper, right. So, right, so the usual example is this. that is one, okay. I forget how the other one starts, but let us do it this way. That is another, right. So, our density based clustering methods like db scan will return this as one cluster and that as another cluster, right, but k means will completely mess up, right. K means will do something like, okay, this is one cluster and that is another cluster or something very weird, right. But then what happens in the spectral domain is that when I take these data points, right, and then try to project them into the eigenvector space, they actually project into different parts in the space, right. These points will project to somewhere here, these points will project to somewhere there, and I can run k means very easily and recover these data points, recover these clusters, sorry, right. So that is essentially the idea behind doing multiple clusters with spectra, right. And so this is where the unnormalized normalized business becomes important, right. So far we did not have to worry about the difference between normalized and unnormalized, and there are different definitions for the normalized Laplacian, right. So one definition is essentially it is whatever d power minus half means. People remember d, right. So d is the diagonal matrix, so L is this one, so you take this is one definition for a normalized Laplacian. It is also sometimes called the centered Laplacian, okay. And then the other definition I believe is sorry, which is essentially I minus d inverse, I mean I minus d inverse A. Right. Sorry guys, back there, I know I was blocking whatever I was writing. Yeah. So the first one is called the centered Laplacian, the second one is called the random walk Laplacian. So why is it called the random walk Laplacian? So think of what d inverse A means, right. For every entry, if there is an edge between that node I and j, that entry will be 1 by degree of I. So if I am doing a random walk from I, that is a probability with which I will take that edge, right. So I will look at all my neighbors, right, I will be taking a edge with equal probability, right. So that is what the random walk does. So 1 by dij, I mean 1 by di will be the probability with which I will take any particular edge, right. Therefore the second thing is called the random walk Laplacian, and then they use that also, right. And apart from the difference in the definitions of the Laplacians, the algorithms are typically the same, right. So you construct the adjacency matrix, find the Laplacian, find the eigenvectors, then if you are looking at two clusters you do this, if you are looking at multiple clusters you form that matrix there, so that will be an n by k matrix, so form that and then you do k means on the data points, right. The only thing that will change is which Laplacian you are using throughout, right. Good.